I think we have most of the students. Let's start on time. For today's lecture, our plan is to first wrap up timing analysis, like I mentioned on Tuesday. It is a very important topic. And then we'll switch to a new topic. We'll start talking about binary arithmetic. We already talked about how do we do addition a little bit, right? So this lecture, we're going to formally introduce it. All right. As usual, a few reminders. Homework 4 is due tomorrow. And we have posted homework 5 on CMS. Also, I want to give you guys a heads up that for next week, we have 2 lab assignments due. Right? One for pre-lab 3A and one for lab report. Okay, just make sure that you're aware of this. And be sure that you first form groups, right, on CMS before you submit. We're not going to take individual submissions. And I also understand that there's a lot of challenges. Right? There are a lot of challenges doing collaborative work, right, with remote learning, right, with COVID. I totally get that part. So it's totally fine that initially, right, at the beginning, right, you and your teammate work independently on lab assignment is totally fine. But at a certain point, it'd be really good if you guys start comparing notes, right? At least before the submission, you guys should talk and decide which version to submit. Okay, of course, ideally, right, you actually want to collaborate closely. Okay, if you are indeed right both in Ithaca or it's indeed convenient for us to talk over Zoom. Okay, at the very least, right? So this will allow you to learn from each other, right, over these different lab assignments. Okay, so let's talk about time analysis again. These are the important time parameters that we introduced last time. We talk about this waveform a lot, right? We talk about some of these predefined parameters, right? This is the floating, this is the not floating, flip-flop propagation delay, FFPD, right? This is the combinational propagation delay, right? And then we talk about 2 important concepts, setup and how. We're going to look at this again, maybe in more depth today. But first, let me clarify one thing. Last time, there were a couple of very good questions asking about what exactly are these crosses, right? First, we have these hexagons, right, which indicates some value, and basically some value, either 0 or 1. Okay. And last time that I did mention, so if you look at these crosses, this one basically means that so the signal is sort of propagating, right? But let me be more precise this time. So really, these crosses, they are just, you can just treat them as don't cares, right? They just mean don't care, right? We really don't care about what exactly, right, is the output of the flip-flop until this point, right? Okay, same here, right, over here. And I remember there's a question about what exactly is this gap, right? It seems like we already have stable, right? We already have a valid output from the computer logic at this point, right? At this point. But why is this still, right? Why do we still have these crosses over here or X over here? Right? Again, these just mean don't care because we don't really capture the input until this point, right? Until we hit this so-called decision window. And this really means that that the computer output, right? Computer output can be stable over here or can be stable over here, as long as stable right before the decision window, right? Right before this deadline, we are fine. Which means that in this case, right, we can add additional delay to the computer logic, as long as we don't exceed, right? So the added delay does not exceed this part. This is totally fine. Okay, hopefully this makes sense. And let me ask you a few more questions, right? Just want to make sure that first, this is a refresher, right? For some of the concepts we covered last time. Also, hopefully this will lead to some interesting discussions. All right, so here's my goal. I want to achieve a higher clock frequency, basically smaller clock period, right, or smaller cycle time. So this is my goal. Assuming that I can tweak these parameters. Okay. Do you think I would want the smaller computational delay or larger one? You want to get higher clock frequency? Smaller or larger? Very good, right? So this is pretty obvious, right? Smaller. Okay. Next question, smaller setup time or larger one? Again, I'm assuming that we can somehow tweak this. Smaller or larger for setup. Okay, very good, right? Same thing here. We want a smaller setup time, right? Remember this inequality of the equations like this, right? We have FFPD, right, plus T com, right? These two combined, they are basically computational delay, right? The propagation delay, and plus T setup. So this cannot be greater than T clock, which is cycle time, right? The smaller the T clock is, the faster the actual circuit, right? The higher the clock frequency. So of course we want smaller T-com, right? And smaller computational delay, we want smaller setup. Okay, I'm missing the U here. How about this one? You want smaller hold time or larger one? Oh, it doesn't matter. Very good, right? Okay, looks like you guys agree, right? Not relevant here, right? Doesn't matter. For determining the clock frequency, as I mentioned that, right? So when we talk about hold time, it's really about after the clock edge. Doesn't matter here. Okay, right? So you guys are doing very well so far. There is a question, right? Alma's asking why not? Just look at this inequality here, right, Alma? We don't even have hold time over here. Right? The clock is not constrained by the hold time, the clock frequency. And we treat this hold time violation as a separate constraint. Okay, this one maybe requires a little bit more thinking, and also, we need to maybe I need to remind you guys about this clock skew, right? Negative or positive. Negative means that the sending flock, right, is seeing the clock late, right? Positive means the receiving flock is seeing the clock late. All right, very good. So we want positive, right? Positive is beneficial. Negative is, right, harmful. One more follow-up. Okay, for a positive one, do we want smaller skew or larger skew? There's some debate, right? Smaller or larger? Okay. All right, so maybe we don't have to settle this right now. Maybe we can take a look at this right, setup constraint one more time, okay, later on. But keep this question in mind, right? If you're not sure yet, okay, whether we need negative skew or positive skew, or smaller one, larger one, ask me later. Okay. But these are good sort of discussions, right, on the chat window. Most of you are getting this right. Okay. Let's look at simpler case first, right? This is the quiz question, right? This is 2 input mux. The assumption here is no wire delay, right? Each gate takes 1 nanosecond. Okay. Of course, the long pass, right? The T-com part, we take the max of the T-com, right? It's 3 nanosecond. We have 3 nanosecond for FFPD, right? Oh, sorry, 1 nanosecond for FFPD and 3 nanosecond for setup. We just have to add them up, right? And in the end, the clock period is, right, the best achievable clock period is 7. Okay. If it's still not too clear to you, right, so whether we need a larger setup or smaller setup, hopefully this is clear from the inequality here, right? If we have a smaller setup time, effectively, the clock period will be also, the best achievable clock period cycle time will be also shorter, right? Okay. Oh, so you're saying that, Ambrose, you're saying that there's inconsistency with my quiz, the assumptions. I'll double check. Okay, but again, this is just example. When we grade it, we will actually look at the question again, right? Thanks for a good catch. I'll double check. But coming back to this example, right? Coming back to the example, hopefully this is clear, right? If it's we have a smaller setup, so most likely it's going to lead to a smaller clock period. Okay, and we'll come back to this, this is setup time person. All right. This is related to the last question, right? In my previous slide, I asked you guys about, do you prefer a negative skew or positive skew? Okay, the answer is, right, we prefer a positive skew. But let's look at negative skew first. It's harmful, right, for meeting the setup time constraint. Why is that? If you look at this inequality, right, I'm not going to repeat right, how we end up with this inequality. Right, check out my notes and also the lecture, recorded lecture last time, if you don't remember. But this is the inequality, right? This is the equation that we derived. So first, we have, right, this term on the right-hand side, right? The reason that this is called a negative skew is, see here, we do have a minus sign. That's why it's called a negative skew. And also, why are we not using the mean skew? Why are we using the max skew here? Any ideas? Why is this the worst case? We always want to take the worst case, right? When we consider this kind of a constraint. We want to meet the earliest deadline. Yes, right. So that's the worst case, sort of, right? Basically, that's. But let me be more precise. So really, if you look at this inequality, if we put in mean skew, we have something like this, right? Agree, right? So this term, right, t clock minus t skew max is no greater than, right, t clock minus t skew mean. Agree, right? This holds, which means that, if we cover max skew, the mean skew is already covered with this inequality. Right? Hopefully this is clear. Right? Basically, this is indeed the worst case condition over here. We really don't need to consider skew mean, because the moment we cover this inequality, this part is automatically covered. Right? And let's try to rearrange things a little bit more. So if we try to move this one, right? Let's focus on this inequality again. If we move this term to the left-hand side, okay, of course, we still have this FFPD and combination delay, right? But we can re-express the left-hand side as something like this. Right? Okay. No magic here. This is a basic, just a very basic rearrangement. But what does this mean? It means that the reason that I put the parentheses here is that this sort of means that the effective setup time, right? This effective setup window is sort of a wider, right, or larger. Makes sense? We treat this whole thing as one term, and we treat it as something called effective setup time. So we just discussed, right? To have a higher clock frequency, we want a smaller setup time. But in this case, if we rearrange the term, we have a larger effective setup time. So really, this means that this is harmful, right? This is not beneficial, having this kind of skew. Right? Is it clear? Any questions? If not, let's move on. Let's look at the positive skew. All of you agreeing that, right? So most of you, I think, agreeing that, right? This is good, right? This is good for meeting the setup time. This is good for minimizing the clock period, right? Again, here it's cut positive. It's because we have plus here, right? This is a plus. That's why it's cut positive. And the subtle thing here is we are using mean, not max here. The mean of skew, the minimum skew. Right? Same reasoning, right? Because if you use a skew mean, right, we automatically cover this. Right. So that's why for positive skew, right, for beneficial skew, we want to use the minimum case, which is the worst case. Right. And we can do the same trick again. If we rearrange the term, right, we move it to the left-hand side. Right? This, right, this. So really we have T setup minus, right, T skew. So effectively, the setup time window is shorter, which is good, right? That's why it's beneficial. All right. No. Of course, the other way to look at this is, in the previous case, effectively the clock width, right, is narrower, and in this case, the clock width is wider. Okay, that's also good for meeting the setup time constraint. All right, if this is clear, let's look at some more questions. Let's look at hold time violation. To avoid hold time violation, what would you prefer? Same set of questions. Smaller combination delay or larger one? This is hold time. Very good. Larger, right? Okay, we want larger delay, smaller setup or larger one? Second question. Larger? Do we need to care about setup time? Then we look at the hold time violation. Okay, very good. Again, not relevant. Okay. Next one. Smaller hold time or larger one? Smaller or larger? Okay. Very good, right? I think we have a consensus. We do want it to be smaller, right? This is sort of to the opposite, right? We'll see. Actually, the last one this is sort of to the opposite, right? We want a smaller one. Last one is actually the opposite, negative or positive. Right? In this case, it's negative. We'll see why this is the case. Okay. Right. So we'll see also, do we want a smaller skew or larger skew? All right. Hold time. Okay, with the clock skews. This is something that we did not discuss last time, right? So let me try to be a bit slower. Again, so over here we have positive clock skew, which means that the receiving clock, okay, which is FF2, is seeing the clock late, right? Seeing the clock later than FF1. That's where we have this positive clock skew. What's the trick last time, right? So when we analyze this, right, what I mentioned is we want a reference clock, right? We also want to define the reference time. So let's do T0, right, equals 0 here. Right, I'm looking at clock 1. Right, I pick out this edge. With this defined, what is this? What is this time, this point? What is this edge? With respect to the reference time. We have a skew, right? This is basically 0 plus T skew, right? That's it. And we care about, let's focus on FF2, right? We care about hold time, the hold time constraint. So that's where we need to look at the this window, this small window defined by t hold after the clock edge. Over here, we have this t hold, this window, and what is this point? Again, with respect to the reference time. What is this? This one. Okay, we get t skew plus t hold. Okay. All right. So basically, this is a new hold time window, right? With the skew. Right. Really, this is the new hold time window is t skew plus t hold. So effectively, this hold time window is widened, right? Which I think you guys agree that this is bad, right? This is harmful for meeting hold time constraint. Right? Okay, so if we agree on this, then the constraint, right? This inequality is pretty straightforward. Right? We have this one, right? This is the hold time window, right? This is a new effective hold time window on the right hand side, and this is the so-called contamination delay. Right? This is the shortest path. This is where we take the minimum propagation delay for FFPD and also combinational logic. Right? Also notice that we are taking skew max here, because if we do this, we can automatically cover everything else, right? That's why we take skew max. Any questions? Do you guys agree? Right? This is harmful and is opposite to the setup time. For meeting setup time, we want positive clock skew. And for hold time violation, we want actually negative skew. So hopefully you guys now see the trade-off, right? You know, this designing this kind of circuit is not that trivial. All right, so negative clock skew, I don't even need to show you the waveform, right? Hopefully this is clear enough. This is beneficial because now this ascending flop, right, which is FF1, is seeing the clock later than FF2. With that, we have a negative skew here, okay? And we take them in here because this one covers t hold minus t skew max, okay? And effectively, in this case, the hold time window is shorter or smaller, right? Which is more challenging. Okay. All right, so there's some question. Wouldn't it be bad if the skew was negative and so big that the hold time happens before the clock edge? Wouldn't it be bad? Yeah, sure. So basically, Alma, you're saying that there's this, in some cases, the whole thing is just infeasible, right? That's what you're saying.
Oh, I guess that's what I'm saying. I just mean like if on the waveform the whole time happened before the first clock got to the, like if clock 2 was shifted so much that it was to like the positive edge, or yeah, that T hold happened before.
Right. So basically, you're saying that the skew is too large, right? In some cases, this is simply infeasible, right?
Mm-hmm.
There will be such a if you design it incorrectly, right? So that's why I'm saying this is a trade-off, right? So we actually need to be very careful with the skews when we design the chip, right? When we lay out the clock network. So we need to make sure that this does not happen. Right? We need to make sure that we meet the setup time constraints. We also need the hold time constraints.
So
we want to avoid the scenario that you just described.
So the skew can't be bigger than T hold if it's negative?
Skew cannot be bigger than T hold. Skew can be bigger than T hold, right? I'm just saying that we want to make sure that, right? So this one, right? So it's really about this two, right? So we need to make sure that the minimum computational delay is no less than T hold plus the skew, right?
Okay, yeah.
Right. If this is too large, right, then we may not be able to design a circuit, right, to make this inequality hold. That's bad. It's really about two things, right? The computation delay, the minimum computation delay, and the hold time, right? Okay. All right. If it's still not clear, let's do a quick exercise. So here we are analyzing the hold time with the clock skew. So first, can you guys tell me, like, is this a negative skew or positive skew? The clock may arrive at FF2 up to 3 nanoseconds later than FF1. Is this positive or negative? Very good, positive. Okay, then tell me, do we have a hold time violation or not? Which numbers do we pick up? We don't care about setup time, right? That's something that we already agreed. We don't care about the max propagation delay, right? It's really about the minimum ones. Okay, right. Let's on the left-hand side should be clear, and it needs to be no less than what? Hold time, right? On this one, 1. Yes or no? No violation, right? The skew is 3. The max skew is 3, right? So there's no violation. The constraint is met. Right. Coming back to Alma's question, if this one is 5, or let's just make it 4, do we have a potential hold time violation? Yes, right? Then we no longer have this inequality. Okay. Does it make sense, Alma?
Yeah, that makes sense.
Okay, great. Okay, any more questions about time analysis? Just to repeat, right? It's really about one thing to look at the things. It's just to analyze the effective setup time and hold time, right? In this class, I really want to encourage you guys not to memorize things, right? You know, whether positive is harmful or negative is harmful, whether it's for setup time or hold time. Let's try not to do that. Okay, let's try to understand the intuition, right? And here's the intuition. The reason that in this case, this is right, whether it's a harmful or beneficial, it's really about, you know, whether the effective setup time or hold time window is larger or smaller.